we'll cover stress and strain. This is part of the engineering syllabus that deals with a few different types of stress and strain. So we have shear, compressive and tensile stresses. We have engineering and true stresses. These you have to recognise what they are and what the different applications are. You've got yield stress, proof stress, toughness, Young's modulus, Hooke's law, and the applications to engineering. And these are covered in the graphs. You got your factor of safety and your stress strain diagram, which links into the graphs here. And you have to be able to apply mathematical and graphical methods, and you need to be able to understand how they apply to real life situations. Alright, so what is stress? Stress is the relationship between an applied load and a material's cross-sectional area. So if you have a material, let's say it's a cylindrical item like this, and you've got a force acting down on it, the stress is the relationship between this force and the cross-sectional area. So it's acting down on that way. So if this is going to be in compression, then your compressional force will be the force over this area. So if this has a diameter of, let's say, just diameter units, you would have a cross-sectional area of pi d squared on 4. And that would give you your stress. So stress is measured in pascals. So we have our force, which is in newtons, over the area, which is in meters squared. And that results in pascals. And then we come to strain. So strain is the relationship between the change in length of an object when it is under a load. So a constant load, if it's extending in length, so if it's being stretched out, say it's in tension, then it's going to have a strain amount. So it's the distance it extends divided by the original length. So if we have that same example as before, if we have our cylindrical thing here and we compress it and it goes down this far and now it takes on this shape, then this distance here is the distance it's extended, and this distance here is the distance that it was originally. So you find the relationship between those and it gives you the strain value, and that is a constant value. As you can see in this diagram, we can get a graph that relates the stress to the strain, how those change as the stress increases or as the strain increases. So types of stress. So you can have true stress or you can have engineering stress. So true stress, as we stated by the formula before, stress is always force over area. And this area is what determines the difference between true stress and engineering stress. So true stress is always going to be based on the actual cross-sectional area at that point in time. So when you have, let's say you've got a rod like this, and it's being stretched, it's in tension this way, the bar is going to extend. Let's say it extends this much. When it's extending, since it's not gaining any extra material, this width of the beam is going to decrease slightly. You'll see that if you stretch a piece of dough, in the middle it will start to decrease in diameter. And for true stress, you're taking the actual value of that diameter. So as it stretches, the diameter you're using in your stress calculations is reducing as well. Whereas in engineering stress, you're always using the original diameter. So the original cross-sectional area is always used to calculate the stress. And this essentially allows for a greater factor of safety, which we'll cover in a second. So you can have tensile stress, which is when it's being pulled apart. So when it's going that way. You can have compressive stresses, which is when it's being forced like this. And then you can have shear stress, which is your sliding force. So if we have two items like that, one's being pulled that way, one's that way, you'll have shear stress in there. And it's important to know the difference between these types of stress, as it determines what area you're using for your calculations. So a helpful way to remember it is the area that you're taking is always going to be perpendicular to the force that's applied. So if we have this stress acting this way, then the plane that we want the area to be from is going to be this way. So we're going to have a cross-sectional area like that, if this was a cylindrical beam. And then for compressive stress, it's the same. We've got forces acting that way, so the area that's going to be effective is going to be a cross-section through there. So it'll look something like this. Whereas with shear stress, you've got two forces acting sort of that way, which is applying like a force kind of going like that. And since we've got two items, we're not really going to be able to take a cross-sectional thing like that very easily. So what we have is it'll be this area where it's actually experiencing the force. So we'll get into that calculation in a second. So types of shear stress. So you can have double shear or punching shear stress. So as we saw in the diagram before, shear stress can be a little bit confusing sometimes as to where you find the area for it. So when you have something in double shear, you have two areas that are actually being affected by the force. So as you can see, if we have a metal segment like this, so it's comprised of three things, and we've got essentially two forces acting on it. So we've got one acting that way and one pulling it to the left. We're going to have 2 points where this screw here is going to be experiencing some shear force acting through it. So we've got one right there and another one right there. So those are the 2 points that it's going to be subject to stress. So essentially all we're doing is we're timesing the diameter here. So if we were to take the cross-sectional diameter like this, we have to times that by 2 because we actually have 2 of those areas that have the force spread across it. So it's a similar concept with punching shear stress. So if you had a plate like the one in this diagram to the right, and you wanted to work out, well, what's the shear stress acting when I'm trying to punch a hole through this piece of metal? Well, you want to know, well, what's the rubbing force? So if we've got this plane being forced downwards, and so this plane is going to try and push a reaction force upwards if this piece is going to be punched downwards, which means we're going to have a rubbing force like along there. So instead of taking just the top diameter and using that for our area, so we're not wanting that area, we actually want the area of this bit here. So we want this blue shaded area, which is now an orange, because that's going to give us the shear stress when we're punching. If we wanted the compressive stress, then we could just use this top area here. But since it wants the shear stress, we have to be sure that we're using the area of so we want the circumference of the top, and then we want to times it by the thickness of the piece, and that'll give us that area inside there that's actually being subject to the shear force. So stress-strain diagrams. If you have a stress-strain diagram for mild steel, it might look something like this. So in metals, you'll typically get a region that goes straight up and has a constant gradient, so it's a linear line, and then it'll get to a point where it starts to kind of bend, then it'll like dip for a second and go up until finally coming to an end like that. And what this shows us is how the material is behaving as it's going through increased stress and increased strain. So initially, when your stress and strain value is 0, there's not really anything going to be happening in this piece of metal. But as you increase the stress, the strain will increase proportionally until you reach the elastic limit, and then it reaches a point where it will start to experience some deformation. So this means as it extends now, it's not going to return to its original shape. So from the yield point, it's no longer going to retain its original shape once you let go of the load. And from there, you're going to experience more deformation, and then a decrease in diameter of the specimen until it finally breaks or fails. So let's get into this with a little bit more depth. So the Young's modulus, also known as the modulus of elasticity, can be used to determine the stiffness of a material. So the Young's modulus is calculated from this linear portion here. So where the stress is proportional to the strain, you take the gradient of that line, so it'll be rise over run, so stress over strain will give you Young's modulus. And Young's modulus on the formula sheet is represented by this letter E, and it is in pascals. So to find the modulus of elasticity, to work out the stiffness of the material, you find the gradient of that line. The greater the gradient is, the stiffer the material will be. So the elastic limit, as I mentioned on the previous slide, you have your linear portion here. So we have our stress value there, and we have our strain axis there. And as you go up, you get to this point where it stops being linear. And that point where it immediately stops being linear is the elastic limit, also known as the limit of proportionality. And this is where the last point where the stress is directly related to the strain. So before this zone, you essentially have your elastic zone. So all the area underneath the graph up to the point of the elastic limit is your elastic zone. So if a material is stretched within these stress and strain values, it will retain its original shape. So say, for example, you have a beam like this, you're stretching it outwards and it extends a little bit. Let's say it extends to here, and then you let go, the force is gone, it will snap back into shape just like that, and nothing will be damaged. So then as we progress along the graph, you get to your yield point. So we have our elastic limit just there, and you keep going and it starts to get this little curve, and you get like a little bump here. Now yield point is where the material continues to stretch without an increase in load, and from this point the material will no longer go back to its original shape, but will be permanently distorted. So as you can see, it's kind of increasing in its stress amount, and it's starting to kind of level out. So right here, it goes down, so that means we haven't actually increased the load that's applied to the material, but the strain in it is continuing to grow, so it's continuing to deform even though there is no strain to it. So from the edge of the elastic limit, so we have our elastic limit line there, all the way up to this point here, which is the ultimate tensile strength, and it keeps going past that line all the way to the end of the graph. You have your plastic zone. So this is where if the material is in this region, it will be stretched and will not go back to its original shape. So if we have our beam like that, it's being stretched outwards and it extends that much. If you let go of that beam, it will stay stretched like that. It's not going back to its original shape. Alright, ultimate tensile strength. So this is the highest point on the stress strain graph, and it indicates the maximum stress the specimen can endure before it fails. So if you load it beyond this point, it is going to experience failure, and that's important to know when you're constructing something. And from the ultimate tensile strength point all the way up to the point of failure, the area under that graph is known as the necking region, and this is where the material undergoes a localized reduction in cross-sectional area. So if we're stretching a specimen like this, we know that as it gets to the ultimate tensile strength point, once it goes beyond that, the diameter of the specimen will start to decrease. So it will get thinner and thinner and thinner until eventually it snaps. And that snapping point is known as the failure point. So it's the point at which fracture occurs, and the greater the toughness and the material has, the more energy it will take to break the specimen, so that failure point will be further along. So this is a really important point to note, because you don't want to ever subject something to a situation where it is likely to reach that failure or breaking point. So essentially, you never want to load something beyond the ultimate tensile strength point, because then there is a great risk of failure, and that's not great for safety. So one other thing to note is Hooke's law. So Hooke's law relates the linear section of our graph again. So, and it states that stress is directly proportional to strain up until the proportional limit. So that's essentially stating that in materials that obey Hooke's law, the first section up until that elastic limit it's going to have a linear line to it, and that's essentially stating that the amount of deformation that will occur in a material will follow a linear relationship. So you can tell if something obeys Hooke's law. If it obeys Hooke's law, it'll have a linear section up until that elastic limit. So your factor of safety in stress strain diagrams. So this is when you're doing some calculations. So say you want to calculate the stress in a material. So you've got your force over area, but the builders say, well, actually, I want to make sure that it will never be loaded to half the amount it can actually withstand. So let's give some values to our stress value. So let's say that stress is 100 megapascals. So that's what the actual specimen can handle. It can handle a load all the way up to 100 megapascals. Your factor of safety will divide that value by the factor of safety and give you a reduced ultimate stress limit to make sure that you're not going to be loading it to a point where it's likely to fail. So the factor of safety must be greater than 1, otherwise it would not result in a reduction of the stress it can receive. So usually the factor of safety is around 2 to 3 for most applications in civil engineering. So what that means is what it will be loaded with is going to produce half the amount of stress it can actually take, and this means that it is less likely to fail because it's never being loaded to what it can actually withstand, which means, say if you have a bridge and you've said that the bridge can hold as many as 50 cars on the bridge until it fails, then you would set the limit for how many cars can actually be on that bridge as 25 if you have a factor of safety of 2, which means just in case you end up getting 26 cars on the bridge, it's not going to fail. And if the factor of safety is 25, then if the factor of safety is 2 and you're only ever loading it with 25 cars, then it's very unlikely it's going to hit 50 cars and actually fail. So that's what we do for factor of safety. Just remember, as always, the stress value divided by the factor of safety, and that will help you with your calculations. Proof stress. So this is another way of calculating the elastic limit of a material. So in the previous diagram, we saw for a metal that your graph might look something like this. So it has your linear section, then it goes for a bit of a bump, and it goes like that. And we know that the elastic limit is going to be right there at the end of the linear section. However, not all materials follow this linear structure at the start, which means it's difficult to tell where that yield stress will be. So where that point will be, where the material will stop essentially bouncing back into its shape. So for something like a brittle material, you might have a graph that just looks like this, and it's not really linear very much at all. You can see that there's kind of a gradient, but it kind of curves, and you don't really know exactly where that more linear section ends. So to approximate where our elastic limit is going to be, all we do is we go to the strain axis, and there'll be some values labelled on there, and you go up to 0.2% strain. So at 0.2% strain, you plot a point, and you essentially want to mirror as closely as possible the gradient of this slope here, and then you're just going to extend it across like this. And that point where it touches the graph there, that's going to be your proof stress, and then your proof stress can be used for calculations that would ordinarily use an elastic limit or a yield point. It's an artificial approximation, but it helps to make sure that we are understanding the nature of how this material will respond, even though we don't have a defined limit from the actual graph that's formed. So some different graphs that you might come across may look like this. So if you have a very brittle material, such as a ceramic or glass, it is likely that it will fail quite early. So most of the time, if you drop a plate, you're not going to experience the plate going like all soft and mushy and deforming before it snaps. It kind of hits this point where once you stress it a certain amount, it just fractures. And you'll know for that with glass as well, if you hit glass with a hammer, it doesn't bend out of shape, it just shatters. So you'll have a failure point that kind of just looks straight like that. And if you have something that is soft and tough, so that means it is strong for a little bit, but then it starts to bend and mold out of shape, and it'll look like that. So if you got a piece of copper wire, for example, it might look like this, where it's stiff for a bit, and then it kind of starts to stretch out of shape. A good test that you can do to kind of see this happening is if you get a paper clip and bend it a couple times, you'll see that it slowly starts to deform and lose that structural integrity, and the diameter will actually start to decrease until it eventually snaps. So non-linear elasticity, so something like a rubber band, it'll stretch for a little bit and bounce back into a shape. So if you did your proof stress, it might look something like that. That'd be your limit there, and then eventually it would just snap. So it doesn't have much toughness because there's a low area underneath this graph. And aluminium, so you might have something with no defined yield point, so it might look like that. And something with Chauvet-Hooke's law will always have a linear portion, just like that. And then this graph here, the final one, is just displaying plastic deformation, and that it is kind of having that curve there. And one other thing to note is the total area underneath your stress-strain graph is what gives the toughness. So the toughness is the amount of energy that a material can withstand before it fails. So this whole area under here, if you find a calculation for that, that indicates how tough the material is. So the greater the area, the tougher the material will be. Toughness is the total area under that curve. So that covers stress and strain diagrams.